All right, we're up and running. And as usual, we want to begin with any questions you had on, what is it, 3.2. Questions on 3.2. '88. Got it. All right, number 88. We'll take a look at that. Let's see. I'm going to go to a blank slide here. And then what I'm going to do is just kind of grab the question here. If I can find it. Okay, true or false? Yeah. So let me grab this. Okay, so 88. So if y equals pi squared, then dy dx equals 2 pi. So Damon, what did you think? Did you do true or false?
I think you're looking at 89. That was 89.
Oh, I'm sorry, 88. You're right. 88. If f of x equals g of x plus c, then f prime of x equals g prime of x. So did you say true or false?
I mean, I couldn't figure out why it would be false.
Yeah, I think you're well, and is so because that's a constant afterwards.
Yeah.
We know that the derivative of that is going to be 0. So are you what did they say in the back?
It's an even. It's not in the back.
Oh, okay. So I would totally agree with your it's got to be true.
So then would 90 also be true? I think
90. If y equals x over pi. Well, here, let's just take a look at that. I mean, we could think of that like this, couldn't we? And the reason I wrote 1 over pi, because then it's just a constant, right? And in effect, it doesn't. So when you take the derivative, what's going to happen? The constant just sits out there and you take the derivative, so you would, I mean, wouldn't the answer be, here, let me rewrite this with an f of x notation here. So that one could come out to this, Damon, for number 90. And so, yes, it does appear to be true again.
Okay, and that's the same, yeah.
Yeah, it is the same kind of concept, right? Welcome on board, Brandon. And
thank you.
Good to have you. Yeah, we were just going through looking at 88 and 90 from the 3-2 assignment. Thanks, Damon. Other questions? Oh, we have one from David Wilson, 35. Thank you. It's hard to spot all these things. So let's take a look at 35. So let's insert a page here. Okay, 35. Okay, make that a little bit smaller. All right, so finding the slope of a graph. In exercises 3138, find the slope of the graph of the function at the given point. Use the derivative feature of a graphing. Okay, so they're saying go ahead and confirm it in a graphics. So 35 is f of theta equals 4 sine theta minus theta. Okay. So when we take that function, what's its derivative? So what's f prime of theta? Well, so the first part, this 4 sine theta, we know that 4 is a constant and 4 will just remain, right? Now it's kind of just leave it for a while and do the rest of it. What's the sine of theta? What did we learn is the derivative of the sine? That's the cosine. So this first part becomes 4 cosine theta. And then if you think of theta as an x, what's the derivative of x? 1. Sometimes hard to think of when you have a different letter in there, but that should be our general derivative. So now the question is, what's f prime at 0? So what's the cosine of 0? That's a 1. So 4 times 1 minus 1, and the answer should be 3. So what we're saying is the slope of the tangent line at the point 0, 0 should be 3. Now, any questions on that before I go on, David? I want to pull up, we'll pull up Desmos and we'll just check it out.
So you always treat the theta as an x then?
Yeah, it's a variable.
Okay, that makes more sense.
And let's just take a quick look at what this looks like. So I gotta write this down here. So 4 cosine theta minus theta. All right, and I'll probably call it x, but let's do it in Desmos. So 4 cosine x minus x. So here's the function. And the question is at the point 0, we learned, yeah, well, you know what? We're going to have to finish it. But because if you look real closely here on the graph at 0, you can see there is a negative slope there. I don't know, but you know, I'll tell you what. Let's go back to the problem and let's go beyond what the problem asked and let's find the whole equation. So now that we know the slope is 3, they didn't ask you to do this, but I want to do it to demonstrate on Desmos a little bit better. And we found the slope is 3. And then we have the point 0, 0. You know, that doesn't seem to match because that's a negative slope, isn't it? Okay, what did I do? So b equals 0. Sorry if this is so sloppy here. Let me neaten that up a little bit. So b equals 0. So I'm saying the equation is y equals 3x. But that doesn't seem to match because if we look at our graph, it appears it's got a negative slope. So I'm trying to figure out what did I goof up on here. So y equals 4 sine theta minus, we took the derivative, 4 cosine theta minus 1. And then we took the derivative at 0. Cosine of 0 is 1. 4 times 1 is 4 minus 1 is 3. Oh, I was at the wrong point, wasn't I? Yeah, 0, 0, there is no point. Something is goofed up here. I don't even have 0, 0 being on the graph. They claim 0, 0 is on the graph. All right, let me see. I call that 4 cosine x minus x.
Isn't that the derivative and you have to graph the actual graph?
Oh, thank you. Absolutely correct. So what was the original? 4 sine theta minus theta. Thank you, David. So 4 sine x minus x. Yeah, there we go. And now we found that the graph was 3x. And sure enough, at 0, 0, we did do it right. The slope of the graph is 3, and it's nice and tangent. Now, some of you might scream and yell a little bit because do you notice that the tangent line actually crosses the graph? You know, if you look, it's above the red graph up here, but it's below the red graph down below. So actually, it's a tangent line that crosses, but I mean at 0, 0, it's tangent. So that can be, sometimes that can make people a little bit confused and upset. Okay, so we've confirmed that one. Let me check my window. 35 is the one we did. Is there anyone else who has a question on the previous assignment? Okay, we're going to get a start on the new, and you probably noticed from my words, a start. This is probably going to be a 2-day lesson. So here's the lesson in the book, 3.3. So far, the rules have been really easy, haven't they, guys? I mean, the power rule is really easy. The constant multiple rule is really easy. Everything seems to be working just like you'd hope it would. And it's extremely easy to do, even in your head. Well, we're going to be moving to some rules that are a little bit hard to execute and take a little bit longer to do. They're called the product and the quotient rules. And then the book also throws in a third topic, and that is higher order derivatives. So we have 3, kind of the product rule, the quotient rule, and what are these higher order derivatives and how do we do them? So that's the topic. You can see those are listed out separately, including applying that to trigonometric functions. So that's where we're going to go today. So you can guess, why do you think we have these rules? Well, we will need them to do certain types of derivatives. So not everything is so neat as it has been up until now. So sometimes you have 2 things that you cannot multiply out. So if you have 2 functions that are multiplied out, as indicated on the left here by what you see in parentheses here, is the product of 2 separate functions, function f and function g. And we're supposed to take the derivative of a product. So that's why it's called the product rule. And here it is. And I'm gonna give it to you in words. It says take the first function times the derivative of the second function plus the second function times the derivative of the first. And that's how I remember it. Okay. So one more time, if I have 2 functions that are multiplied and I can't multiply them out, then I have no choice if I need the derivative to use the product rule. And the way to do it is take the first function times the derivative of the second function plus the second function times the derivative of the first function. And you'll of course have to know that. All right. So that's the rule. can you, hopefully you can see from looking at it that the g prime of x, that's their way of saying the derivative of the second, right? Did you catch the prime notation there? Why did they use that? And then over here, they use the Leibniz notation, the d dx. Well, we don't have really a single letter for the combination of these two functions, so this works out to be the handiest. All right, let's look at an example here. And they have this nice example in the book. You see up on the top here, we've got two functions. Now, by the way, just let me say this right up front. Could we multiply these two? Yes, we could. So we're showing you the rule on a function where we actually could avoid using the rule. But that's because it's a little bit easier to show you on, okay? So this is a problem that actually we could avoid using the product rule, but I'm showing you how to use the product rule on this, and then later you'll see some functions where you literally cannot multiply them out first. Okay, anyway. So you can see we have two functions here. What's the derivative say? It says take the first. I like the way they showed this up. Take the first, multiplied by the derivative of the second, plus the second times the derivative of the first. So they're just, we haven't done any derivatives yet, but we're just showing you how we're applying the product rule. So the first, okay, what's the derivative of the second? Derivative of 5 plus 4x. Oh, that's just 4. Oh, that was nice and easy. Plus the second, 5 plus 4x. And what's the derivative of the second here? 3 minus 4x. Okay, then just multiply those two sides out, add them together. Voila, we have our derivative. Okay, so again, you're probably thinking, why did we do that when we could have multiplied it out first? And in fact, that's what they're showing you. Look, what if we'd have multiplied this out first? Well, then you would have had this. And now what's the derivative? Negative 24x squared plus 4x plus 15. Notice we got the same answers. So all that's doing is showing you, oh, I forgot to turn the pictures off so you can see a little bit more. Sorry about that, guys. So here we could have avoided using the product rule, but I used it, the book used it to kind of gently get you into it. Now, you notice what it says on the very bottom there? In our next example, you have no choice. You have to use the product rule because you can't multiply them up. So that's what we were trying to, warm you up for. So let's look at this next example. So look at example 2 at the top there. X times e to the x, that's a product. Well, why can't we just multiply them out? Well, you can't. There's nothing you can do to simplify that, is there? That's already, so we have no choice because we have two things being, by the way, what if the function had been y equals 2 e to the x? Well, then it's just a constant, and we learned in the constant rule you can just let the constant be. But this is not a constant right here, right? And so that's why this behaves differently. Hopefully you're seeing that. It's another variable, x e to the x. So here on the right, we didn't have to do any product rule because that was a constant. But when we don't have a constant, okay, we don't have a choice. So here we go. Let's use the product rule. The first times the derivative of the second plus the second times the derivative of the first. So it's that same rule. And now, you know, we got some easy stuff here because when you go back to the beginning, what's the derivative of e to the x? Of course, it's itself. All right, plus the second times the derivative of x. Well, the derivative of x is 1. So you could just say we could just say x e to the x plus e to the x. That would be correct. Or we could factor out the e to the x and get the answer that the book has. This derivative would not have been possible without the product rule. So once again, why are we showing you the product rule? Well, it's necessary, yeah, obviously, or we wouldn't make up a rule. Let's look at this example 3, which is, again, needs the product rule, and this time we have a little trig involved, okay? So we've got, actually, I mean, we've got a sum, that's no problem, but here's the product right here. Those two things in the first part of this expression, 2x times cosine x, there's where we need the product rule. I mean, we know how to do this already. That's old stuff, but this is where the product rule is necessary. So let's use the product rule. The first times the derivative of the second plus the second times the derivative of the first. We'll get to this one over here on the right later. So what's a derivative of the cosine of x? That's minus sine of x. What's the derivative of 2x? 2. And then I guess we eventually have to get to this. How do you take the derivative of that? Well, the derivative of the sine is minus the cosine. I'm sorry, it's the positive, the cosine of x. So negative 2 times the cosine of x. So this this one comes from our non-product rule portion. And okay, then can you do any simplifying? Well, it turns out this whole section right here becomes what? 2 cosine x minus 2 cosine x. So that just becomes a big fat 0. And all that's left, derivative, is over there on the bottom left. So again, we couldn't do this without the product rule. All right. I'm going to nail you with another. Now comes another rule, and you're not going to like this one because it's a little bit more complicated. This time we have the quotient of two functions. Quotient, of course, means to divide. So you see here we're trying to take the derivative of one function divided by another. And here's the rule. You take the denominator, the function in the denominator, times the derivative of the function. I'm not going to read the function each time, but you take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Sorry, can't get that any easier. Of one function divided by another. Denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. I mean, that's basically what they have written up in that paragraph up there, okay? I mean, yeah, you see it up there. So if you look in your books, I don't have a page handy, but if you look in your books, you'll, of course, this is from the book. All right, should we try, let's try applying this. So here's a function. You know, the first thing we should maybe do, since the quotient rule is not a real fun thing to use, is it possible we can avoid it? So, by the way, this is not a bad thing, but when you look up here, is there anything we could do to simplify that fraction? We can't do any canceling because of the minus and the plus sign. We can't factor, so we're kind of stuck. So how could we take the derivative of this thing? Well, we use only choice, use the quotient rule. So we take the denominator, here it is, times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. So this is literally whacking away with that rule. Of course, it simplifies in some cases. Numerator times derivative of the derivative of 5x minus 2 is just a 5, so that's nice. And the derivative of x squared plus 1 is just a 2x, so that's nice. And on the bottom, we're not going to bother squaring that out. Usually you just want to leave that squared. And then it's just a matter of multiplying, the distributive property out and seeing if you can bring things together. So, I mean, the rest of that is algebra 1. Just multiply 5 times x squared plus 1, multiply 2x times 5x minus 2. Watch out for this minus sign here, that applies to the entire quantity. But I mean, other than that, it's just algebra 1 stuff. If you're thinking that's an ugly looking derivative, well, I'm not going to argue with you. But we did it. So you can take the derivative of a quotient. All right. I think I got another one to look at. I can't remember. We'll take a look. Oh, okay. So sometimes you need, and this, I implied this last time. Remember when I asked the question, is there anything we can do to make this, to simplify this fraction before we use the quotient rule? Well, here's a good example. Look at this ugly thing here. We can't, is there anything we could do to simplify that? Well, we could do something to bring that numerator together at least, couldn't we? And so here's where this needs some algebra work before we ever do the quotient rule. So this part right here is all just about doing some algebra to simplify things. So you see how okay, so what they did is they multiplied the top and the bottom by x so that they could get rid of this thing right here. See, when they multiply that by x, then we won't have that ugly second fraction there. So that's an interesting approach. We could have gotten a common denominator and it would have been the same thing, We could have said, 3 over 1 minus 1 over x, and then we could have gotten the common denominator. And that's really what happens, isn't it? You multiply the top by x, and in effect, that's what they did. So anyway, now we have a quotient. And we can't really, but this is much, much better than what they gave us up here at the top. So now apply the quotient rule. All right. So now we can say denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. And then just whack away and do your algebra 1. So again, maybe it's pretty ugly, but there's your derivative. Now, there was more to this problem. Let me just go to the top. It didn't just say find the derivative. It said find the equation of the tangent line. And they gave us this point here. So, we've done those before. So we've got the derivative. Now we need to find the derivative at x equals -1. So as you continue down here at the bottom, so here's our expression. What's f prime at -1? Well, let's plug it in. I mean, you plug it in, it turns out it's 0. So now that you know it's 0, so now you know this term drops away because 0 times anything is 0. And now just plug in the y coordinate, 1. So that's b. So it's y equals 0x plus 1, or just plain y equals 1, as you can see right there. So the rest of that problem, I mean, that's old stuff. How do you find f prime at a number? Just substitute the number in. And I didn't do it, but evidently it just comes out to 0. So the rest, I mean, you've seen that type of thing before. We're always interested in what's the equation of the tangent line at that particular point. So once again, we will continue to do problems like that using our new rules, our new product and quotient rules if we have to. So this is a review. Remember how we already said, hey, what if you have negative exponents? Does the power rule work? Yeah, it does. So for example, I don't know, we don't really have a good example here, do we? Or do we on the bottom? No. Let's, let me take a look in the book and see if we have a good example of this. Whoops, we don't want that. We want to go back to the book. No, they actually didn't give one. I'll make one up. Okay, so for example, let's see, we have enough room here. So what if we have f of x equals 1 over x to the 5th? Do we have to use the quotient rule to solve this? No, because we can write this as x to the negative 5. Can we find the derivative? Sure, we can use the good old power rule, can't we? Because you can take the exponent, bring it down as a product, reduce the power by 1. The only problem is the book doesn't, you know, we don't want to leave it that way, so we'd have negative 5 over x to the 6th. So this is what they're telling you is, hey, you don't always have to use the quotient rule. If you're fortunate like you have here, oh, we can just use negative exponents, and if we have a negative exponent, the power rule still works. So that's what this is a reminder of. All right. Let's find where we are here. Okay. So let's do some trig functions. And these trig functions are going to require us to use maybe the product rule or quotient rule. So here's our problem, example 9 here. 1 minus cosine over sine. Well, there is no way we can simplify that. I mean, it's not true. We could, what they're trying to show you here is these two are equal. This is the same as this. Right, for right now, you know, how do I know that? Because isn't 1 minus, here, let me get my keyboard out of the way here so I can write a little bit better. What they're trying to show you here is 1 minus cosine over sine. Isn't that the same as 1 over sine minus cosine over sine? Isn't that just going kind of backwards fraction work? You know, you guys would all know how to go from there to there because it has a common denominator. But you can also break it up and go this way. Well, what is 1 over sine? Cosecant x. And what is this? I don't know if you recognize that. That's cotangent x. So do you see now where they got this? So those two sides are really equal. Now the question is, what if we took the derivative of the left and the derivative on the right? Would we get the same answer? We should, because they're equal. And of course we do. So here's what they're doing. They're saying, let's do it on the left first. That's what they mean by the first form. So take the derivative of this guy right here. Quotient rule. Denominator times derivative of numerator. You agree with that? Well, the derivative of 1 is 0. The derivative of cosine is minus the sine. So what's the derivative of minus the cosine? Positive the sine. So one more time, denominator times derivative of numerator minus numerator times derivative of denominator, all over denominator squared. Okay, well, sine times sine is sine squared. Over here, after multiplying it out, you get minus cosine plus cosine squared. And you notice, now they told you right here, you got this wonderful identity. Do you remember that one? And don't we really have it with these two underlined blue parts here? So that's just a 1. Well, 1 minus cosine. So here, after simplifying, is my derivative on the left side. So let's do it on the right side now. The right side was cosecant minus cotangent. Okay. So I'm not sure this is clear here. Why is this the derivative? That is as clear as mud. Why is that? What's the derivative of the cosecant? Well, I mean, the way I would do it is what's the derivative of the, what's the derivative of 1 over the sine? So I'm not sure I'm going to have to think about this one. Right now, I can't see this. One of those leaps by the book. Anyway, what they do is down below, you're still not done because you take the derivative of the first part up here with the circle and you set it equal to that, and it takes a little while just to show that they really are the same. But they are. So again, I will come back to you guys tomorrow and we'll talk about this particular one. I don't know. Right now, I'm just not seeing it. Unless that's something they told us to memorize, but I don't think they did. So yeah, I'll come back to you on that one. I just want to make one more point, then we're going to leave the, I think the higher order derivatives. I'll maybe start it, but I feel like we need another day on this. So what this slide is showing you is finding the derivative is only half the battle. When you're done with the derivative, you usually have to do a bunch of algebra to simplify your answer, and that's what this is all about. So this first column is, they're saying, hey, let's say here are some derivatives you've got in this first column. Well, how do I simplify it to put it in simpler form, which is what the second column is, the derivative after simplifying? Well, the first one is easy. That's just called multiply add. This one is still pretty easy. It's just that, what, not quite as obvious that this thing right here is cosine, is 2 cosine x, and this is minus 2 cosine x, and when you add them, you get nothing. So that, again, pretty simple. What's going on in this? Let me get rid of that. What's going on in this third one? Just multiply and add. I don't know. There's really not a whole lot to show there either. But this one, the one we just did, is a little bit, this one you can't tell. That's really sine squared x. Okay, and then when you multiply these, you get minus, let's see, cosine times 1 minus cosine x, cosine times cosine minus cosine squared, so it becomes minus a minus cosine squared is a plus cosine squared. And then you have this wonderful identity right here that we just used, sine squared plus cosine squared equals 1. So I guess this is just a reminder that and this is no shock, I've been telling you this all along, calculus, a lot of calculus is algebra. And so here's a case that even after you're done finding the derivative, there's a fair amount of algebra to do. And so, anyway, we've talked about that before. Okay. So let's start talking about higher order derivatives. A higher order derivative means basically after the first derivative, you can go on and take the derivative of the derivative, which we call the second derivative. And then you can take the derivative of the second derivative, and we call that a third derivative. So you see them here listed on this. They go as far as, well, they go all the way down to n. So do you see this little chart here? So here's how we would, that's the notation. We know that's the first derivative. You can write that this way or this way. By the way, this last column, I don't think I've ever seen that used. But second derivative, we just say f double prime of x. See that double apostrophe there? This is another way to write it. Here's how you write the second derivative in Leibniz notation. Third derivative, fourth derivative. Notice we changed, otherwise we'd have a picket fence for apostrophes. Now they just put a little 4 in parentheses right there. Nth derivative. So after we get to 3, then we go to this little number in parentheses notation. So the classic example of this is when you take a falling body, or we talk about gravity, and this is a great example about the gravity on the moon as opposed to the gravity on the Earth. You probably already knew this, that remember maybe, but the gravity on the moon is 1/6 as large as it is on Earth, and so when the astronauts were up there, they could hop around and stay in the air longer. What was it, Alan Shepard? I don't know if you remember this. He actually took a golf club along because he wanted to see that he could hit a golf ball 6 times further, and he actually did whack away at one. So anyway, yeah, David's, and remember, I don't know, I mean, David Scott demonstrated that you could drop a hammer and a feather. Of course, there's no atmosphere on the moon, so there's no air to take a feather and make it, feather its way down. It would just fall directly. So a hammer and a feather fall at the same rate of speed. Here is the distance equation. Whoops, sorry. Here's the distance equation. Sorry, I'm having a little trouble selecting here. There is the distance equation for where is an object after it's dropped. Okay? And that's for the moon. So S of t is simply the height in meters, and t is the number of seconds it takes for it to fall. Okay. So that's a distance equation. When you take first derivative of the distance, which you see right here, s single prime, that'll change distance into velocity. And when you take the second derivative, that'll give you the acceleration function. And in fact, remember, I think I mentioned this, if you take the third derivative, it gives you something called the jerk. But it doesn't apply here, so we won't do it. Well, look how easy these derivatives are. I mean, if the equation right here is negative 0.81 t squared plus 2, what's the first derivative? Power rule, negative 1.62 t. 2 is gone because it was a constant. And look at the second derivative. What's the derivative of negative 1.62 t? Negative 1.62. So you wind up, these higher order derivatives, generally speaking, are really easy. Every time you take a derivative, you kind of lose a power, right? So we went from 2 to 1 to a power of 0. And yeah. So anyway, and then if you go down to the bottom, the Earth's gravitational field is negative 9.8. As we just found out, the moon's is negative 1.62. And if you divide, sure enough, the Earth's gravitation is 6 times greater than the moon's. So this idea of going from distance to velocity to acceleration is a very common application problem of higher order derivatives. Okay, so we got about 5 minutes. I'm going to just start doing a few problems. I feel like maybe we need a little bit more time next time to do a few more. But let's just take some of the problems. The first section here, let's use the product rule in order to find the derivative. So remember, what's the product rule? The first times the derivative of the second plus the second times the derivative of the first. Okay, so shall we do number 2? So f of x, well, let's just say f prime of x right away. The first times the derivative of the second. What's the derivative of x cubed plus 5? 3x squared, using the power rule, plus the second times the derivative of the first. And the derivative of 3x minus 4 is just 3. Okay, so now it's a pretty simple algebra 1 problem, right? Just multiply. And then, if possible, combine. And we've got our derivative. So there's the product rule. Now, let's go down to number 6. Try that one. So if we're going to take the derivative, f prime of x equals the first times the derivative of the second plus the second times the derivative of the first. Now, here's where maybe I should have rewritten this as what? X to the 1/2 power times the sine of x. So, shall we, I mean, there's nothing wrong with what I wrote, but here, let's come back here. If I had rewritten it, we would have just said what? X to the 1/2 first times derivative of the second plus the second times the derivative of the first. Now, what's the derivative of 1/2? What's the derivative of x to the 1/2? Let me do it up here. What's the derivative? Here, let's change colors so we don't get mixed up. So if h of x is x to the 1/2 power, what's h prime of x? 1/2, and then reduce the power by 1. And then simplify that, and what do we have? 1 over 2, what? X to the 1/2? So in other words, 1 over 2 times the square root of x. I don't know if we can simplify that anymore, but so basically the first times the derivative of the second plus the second times the derivative of the first. We could get a common denominator. Honestly, I don't know what format the book wants, but we have, you know, this could either be written that way or as the square root of x. And I didn't have the time to look, well, besides I don't have it, it's an even. But so this is correct. The question is, are they okay with those roots? I think they are. That would be the end of that one. We're at time. So I feel like I need to do more examples with you. I need you guys to learn these two new rules. Let me just repeat them again. The product rule. If you take the derivative of a product, the way to do that in the product rule is take the first times the derivative of the second plus the second times the derivative of the first. And the quotient rule, one divided by another. Denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. So start getting those in your brain and then start looking at the core exercises. We will do more examples and have more discussion tomorrow. So sorry, I did a lot of yapping there. Does anybody have a question to bring up before we stop the broadcast? So I look forward to seeing you tomorrow, you 5 faithful people that are here. Thank you for coming. I'll see you tomorrow.